Have you ever wished there was, I don't know, a shortcut? A way to understand these incredibly complex scientific problems. Things like predicting weather, or designing new materials, maybe simulating fluid dynamics.
Or maybe just wishing that those really intricate physics equations could just, well, learn themselves.
Exactly. It sounds a bit like science fiction, doesn't it?
It really does. But, it's actually becoming a powerful reality.
Absolutely. So today we're taking a deep dive into this really exciting frontier where artificial intelligence meets fundamental physics. We're talking about physics-informed neural networks, or PNNs.
Yeah, PNNs. You can think of them as this groundbreaking fusion, really, of scientific computing and machine learning.
Okay, so what are they actually doing?
Well, at their core, PNNs are deep learning models, right?
Yeah.
And they're designed to seamlessly integrate observational data with the fundamental laws of physics. The ones often expressed as partial differential equations, PDEs.
PDEs.
And this integration lets them tackle both forward problems,
Hmm.
so predicting outcomes based on conditions you already know, and also inverse problems. That's where they figure out unknown parameters just from observations.
Okay, so it's like teaching a computer not just what happened, but the why behind it, based on those underlying scientific principles.
Precisely.
Yeah.
Teaching it the physics.
That sounds incredibly powerful. I mean, you hear about applications in fluid mechanics, bioengineering, even quantum chemistry.
It truly is powerful, yeah.
Mhm.
But, and this is a big but, there's a significant catch.
Uh,
The expert guide we're exploring today, it's called An Expert's Guide to Training Physics-Informed Neural Networks. It really highlights that their practical effectiveness, it can be seriously hampered by training pathologies.
Training pathologies.
Yeah, and also by, frankly, poor choices made by users who lack deep learning expertise. It's like having this incredibly powerful new tool, but it's really tricky to master. You can easily misuse it.
Okay, so let's unpack this then. Our mission today is to dive into these challenges, these pathologies, and maybe more importantly, reveal this series of best practices the guide lays out. Things that can dramatically improve PNN training, efficiency, and accuracy.
Right. This guide doesn't just point out the problems. It gives actual solutions, shows state-of-the-art results, and even sets up new, strong baselines for future research.
So hopefully you listening will get some real aha moments, a kind of shortcut to getting well informed on this really cutting edge topic.
Let's hope so.
All right, so we've established PNNs have this huge potential, but the source immediately flags these training pathologies as a major roadblock. Can you give us a sense of what these fundamental problems actually are? What are these networks really struggling with when they try to learn physics?
Yeah, absolutely. The paper identifies three major issues that often plague these conventional PNN models. The first one is something called spectral bias.
Spectral bias, okay.
What this means is the networks, just by their nature, are biased towards learning low-frequency functions. They like smooth, simple stuff,
Ah,
which makes them struggle, sometimes badly, to capture high frequencies and fine structures in the solutions.
yeah.
Think about sharp changes or really intricate details in the physics.
So like trying to draw fine lines with a thick marker.
Exactly that. It's a great analogy. You miss all the details. And that's a significant problem when you're dealing with sharp gradients or, complex physical phenomena.
Okay, that makes perfect sense. So what's hurdle number two?
The second major issue is causality violation.
Yeah.
This comes up in problems that evolve over time.
Time-dependent ones, right?
Yeah. So conventional PINs, they tend to just try and minimize all the errors from the physics equations, the PDE residuals, simultaneously across all time points.
Okay.
But counterintuitively, they often end up prioritizing later times first, even before they've learned the correct solution for earlier times.
Wait, really? That seems backwards.
It is. It completely violates temporal causality. It can lead to just plain wrong, erroneous solutions because the information isn't propagating correctly through time in the model.
Right. It's like trying to predict the final chapter of a book before you've even understood chapter one. The learning path isn't following the actual physics.
Exactly. The physics has a direction in time, and the standard PINN training might ignore that.
Okay. And what's the third critical challenge?
So the third one is unbalanced back-propagated gradients.
That sounds technical.
It is a bit, but the idea is simple. A PN's overall goal, its objective function, has different parts. Errors from initial conditions, errors from boundary conditions, errors from the PDE itself inside the domain. These different types of errors can have vastly different scales, just numerically, and this leads to unbalanced contributions when the model is training. the gradients flowing back can be dominated by one type of error.
So the network might focus too much on, say, matching the boundary and totally ignore getting the physics right inside.
Precisely. It hinders effective learning because the network isn't paying attention to all the pieces of the puzzle equally.
Wow. Okay, it's one thing to talk about these problems in theory, but the guide provides a really compelling picture, literally. Can you walk us through what we actually see? Like in Figure 3 for the Allen-Cahn equation, how does that bring these pathologies to life?
Oh, Figure 3 is a fantastic illustration. It uses what's called a plain PN model, sort of the basic version without any fixes. And you can clearly see first, the initial condition loss just gets completely swamped, dominated by the PDE residual loss. That visually confirms the gradient imbalance we just talked about.
Okay, you can see it right there.
Then you observe the errors, the temporal residuals, being minimized primarily at later times first. That's the causality violation in action.
Plain as day.
And maybe most subtly, but crucially, there was this rapid decay shown in something called the neural tangent kernel, or NTK, eigenvalues. Think of NTK as like a diagnostic tool. It tells you how well a neural network is equipped to learn different frequencies or details. A rapid decay here is a dead giveaway for that spectral bias. The network just isn't built to capture the fine details effectively.
So it's like a perfect storm of all three problems visible in one plot.
Exactly. Gradient dominance, causality issues, and spectral bias, all hindering the basic PIN.
Okay, so given these pretty significant challenges, the good news is the expert guide doesn't just stop at identifying problems. It proposes this core solution, right? A comprehensive training pipeline.
That's the key. It seamlessly integrates recent research developments to tackle these pathologies head-on.
So think of it like a set of finely tuned strategies designed to make PNNs actually work reliably in the real world.
That's precisely the goal. And the first piece, maybe surprisingly fundamental, is non-dimensionalization.
Non-dimensionalization, like we learned in physics class.
Exactly like that. It's a common technique in maths and physics, but here it acts as this absolutely vital pre-processing step before you even touch the neural network.
Okay, but why does scaling everything down to, like, order 1, a reasonable range, why does that matter so much for a neural network?
Well, think of it as setting the stage properly. It's like making sure all your ingredients are measured in, say, grams before you start baking, not some in kilograms and some in milligrams.
Right, avoids chaos.
Exactly. It scales the input and output variables so they're in a sensible range, typically around 1. This is crucial for how neural networks are usually initialized. Methods like LoRa initialization assume this kind of scaling. Without it, you get these huge disparities in variable scales.
And that causes the unbalanced contributions again.
Precisely. Which leads to those unbalanced gradients we talked about.
Yeah.
And the optimizer, the thing actually adjusting the network, struggles to take consistent, meaningful steps. Non-dimensionalization basically improves convergence by making the whole training process much more stable and efficient.
Is there proof of this? Does the guide show it?
Oh, yeah. They highlight the Stokes flow example. It's in the table 4. When they disable non-dimensionalization, the error just shoots up a substantial increase in the relative L2 error. It really underscores how fundamental this step is. You really shouldn't skip it.
Okay, so that's foundational. Get your inputs and outputs scaled correctly first. Then what about the network structure itself, the architecture?
Right. So for the network architecture, the standard multi-layer perceptrons, MLPs, they're still the backbone. But they need some enhancements.
Okay.
The guide generally recommends networks that are, say, 3 to 6 layers deep, not usually super deep, and maybe 128 to 512 neurons wide. But the activation function is really important.
Which ones work best?
They suggest TON or GLU. Very importantly, they strongly advise against using RailU.
Oh, interesting. RealU is so common elsewhere in deep learning. Why not here?
Because its second-order derivative is 0 almost everywhere. And PNNs often need to compute second derivatives, or higher, to match the PDE terms. If that derivative is just 0, the network loses a lot of information needed to learn those complex solutions from the PDE residuals. It basically saturates the learning signal for those terms.
Ah, that makes total sense. The activation function itself limits what the network can represent in terms of physics.
Exactly.
Okay, so that covers the basic structure. Now let's pivot back to one of those pathologies, that tricky spectral bias where the network misses fine details. What's the architectural fix for that?
So this is where random Fourier features, or RFF, come into play. This is a really clever technique.
RFF, got it.
It directly tackles that spectral bias problem. What it does is it maps the input coordinates, like space and time, into high-frequency signals before they even go into the main MLP network.
So you're kind of injecting the potential for high-frequency understanding right at the start.
Precisely. It allows the PINN to then learn high frequencies and fine structures that the basic MLP would just smooth over or ignore completely. There's a parameter, the scale factor sigma, which is quite important.
Awesome.
You need to tune sigma appropriately to kind of match the frequency bandwidth of the solution you're trying to learn. Get it right, and it speeds up training and significantly improve accuracy.
Very cool. And wasn't there another architectural tweak mentioned? Something about weights?
Yes, random weight factorization, or RWF.
Ah.
This one's described as a simple drop-in replacement for the standard dense layers in the MLP.
A drop-in replacement sounds convenient.
It is. And the claim is that it consistently accelerates training convergence and improves model performance.
How does it work?
The core idea is pretty neat. Instead of learning a single weight matrix W, you factorize it into two smaller matrices, like WSV. And this factorization effectively assigns a kind of self-adaptive learning rate to each individual neuron.
Adaptive learning rates per neuron.
Yeah, it helps the network learn more efficiently, adjusting how quickly different parts of the network adapt. It's a subtle change, but apparently quite powerful for speeding things up and getting better results.
Okay, so we've got the data prepped with non-dimensionalization, and we've beefed up the network architecture with things like the right activations, RFF for detail, and RWF for efficiency. Now, let's talk about the actual training process, the algorithms. How do we fix that really counterintuitive causality violation we mentioned?
Right, the problem where it learns the end before the beginning. The solution proposed is causal training.
Causal training. Makes sense.
So these time-dependent problems, the approach is, first, you split the whole time domain into smaller segments or windows.
Okay, break it up.
Then within each window, or as you move between windows, you apply special temporal weights. And these weights are said to be inversely exponentially proportional to the magnitude of the cumulative residual loss from the previous time steps.
Whoa. Okay, say that again slowly. Inversely proportional to the past errors.
Yeah, basically, if the network has done a poor job learning the earlier time steps, meaning the cumulative error from the past is high, the weights force it to focus more on the current, earlier time step. If it's done well in the past, low cumulative error, it can start focusing a bit more on later times.
Ah, I see. So it forces the PNN to learn progressively along the time axis, just like the actual physics unfolds.
Exactly. It ensures the model really masters the earlier time steps before it's allowed to significantly prioritize the later ones. It respects the natural flow of physical information.
That's clever. So the learning truly builds on itself chronologically. Okay, what about that other big training headache? The unbalanced losses from initial conditions, boundary conditions, PDE residuals. You said tuning that manually is a nightmare.
It really is. Imagine trying to find the perfect weighting factors by hand when they might need to change constantly during training, and you don't even have standard validation data for the PDE part. The guide says manual weighting is basically impractical.
So what's a smarter way?
This is handled by loss balancing, specifically using a self-adaptive weighting scheme. The guide recommends a gradient-based scheme as the first choice.
Gradient-based, meaning it looks at the gradients we discussed earlier.
Exactly. It automatically adjusts the weights for each loss term, initial, boundary, PDE, during training. The goal is to make the norm, basically, the size or magnitude of the gradients coming from each weighted loss term roughly equal to each other.
Ah, so it prevents any one term from dominating the learning process just because its raw error values are bigger.
Precisely. It guarantees that the norm of gradients of each weighted loss is equal, preventing the model from being biased towards, say, the PDE term, just because its residuals are numerically larger than the boundary condition mismatch.
Makes sense. Does it need tuning?
They mention using a moving average of these gradient norms to make the weight adjustments more stable, preventing wild oscillations. There's also an alternative mentioned, an NTK-based scheme, which tries to balance the convergence rates of different terms, but they note it's computationally more expensive. So the gradient norm balancing is usually the way to go.
Okay, so it's like an autopilot for balancing the importance of different physics constraints. That sounds essential. And finally, you mentioned breaking down really complex problems.
Yes, that falls under the umbrella of curriculum training. The core idea is simple. Decompose a really hard optimization problem into more manageable subtasks. Learn the easy stuff first.
How does that apply to keyends?
Well, for time-dependent PDEs, especially complex or long-time simulations, they use a method called time marching.
Time marching, like
Yeah.
the causal training.
It's related, but more about breaking the problem itself down. You divide the entire temporal domain into smaller intervals, maybe overlapping slightly. You train a PNN for the first interval. Then, crucially, you use the prediction from the last time step of that first interval as the initial condition for training a PNN on the next time interval.
So you're solving it piece by piece through time, passing the solution along.
Exactly. It significantly reduces the optimization difficulty compared to trying to make one single network learn the entire, potentially very long and complex time evolution all at once.
Is there an example where this is really needed?
Oh, definitely. The guide uses the Kuramoto-Zhivishinsky equation, which is known for chaotic behavior. Figure 12 shows that trying to train it in a single shot just drastically increases the error. Time marching becomes pretty much essential for getting accurate results in such chaotic systems. It breaks the chaos down into manageable chunks.
That's a brilliant strategy for complex or chaotic systems.
Yeah.
What about those singular perturbation problems you mentioned, where solutions change really rapidly in small regions?
Right? Problems where maybe a parameter, like the Reynolds number in fluid dynamics, gets very high, leading to sharp gradients or boundary layers. For those, they use a different kind of curriculum, a progressive approach.
Progressive how?
You start by training the PINN on a version of the problem that's less singular. For instance, you might solve a fluid flow problem at a low Reynolds number first, where the flow is smoother and easier to learn.
Okay, start easy.
Then, you gradually increase the singularity. Maybe you increase the Reynolds number step by step, using the solution from the previous, easier step to help initialize or guide the training for the next, harder step.
So you're gradually introducing the difficulty.
Exactly. This progressive approach helps stabilize the training, allowing the PINN to get a foothold on the simpler aspects before tackling the more challenging, rapidly changing parts of the solution. The guide shows this with the lid-driven cavity flow example in Figure 14. They demonstrate how this progressive strategy lets them get accurate solutions at a high Reynolds number, 3200, where just training directly would likely fail or struggle immensely.
So, okay, we've covered the main pillars of this comprehensive pipeline. Non-dimensionalization, better architectures with RFF and RWF, causal training, loss balancing, and curriculum learning like time marching or progressive approaches. That's a lot, but the paper also details some miscellaneous tips, right? Extra enhancements.
Yeah, exactly. Sort of additional best practices that provide even more robust and optimal performance. They might seem smaller, but they can add up.
Like what?
Well, one key recommendation is about how you sample the points where you check the physics, the collocation points. I strongly recommend random sampling rather than using a fixed grid or full batch sampling.
Why random? Wouldn't a fixed grid be more systematic?
You might think so, but random sampling has several advantages here. First, it reduces memory requirements and computational costs per training step, as you're not evaluating the network everywhere at once. Second, and maybe more importantly, it introduces a kind of regularization effect.
Regularization, like in standard machine learning.
Exactly. The randomness helps prevent the network from overfitting the PDE residuals at specific points, leading to better generalization, meaning the solution is more likely to be accurate between the points you actually checked. It makes the network more robust.
Interesting how that concept carries over. What else?
Another powerful technique, though maybe more involved, is imposing boundary conditions as hard constraints.
Hard constraints, meaning not just as part of the loss function.
Precisely. Instead of having a loss term that penalizes the network for not matching the boundary condition, you actually modify the network architecture itself so that its output automatically satisfies the boundary condition by construction.
How do you do that?
Well, for example, for periodic boundary conditions, they mention using a special Fourier feature embedding layer. This kind of modification ensures the network output is inherently periodic.
And the benefit?
By strictly imposing the condition, you remove that constraint from the loss function. This reduces the complexity of the optimization problem the network has to solve, often leading to faster and better convergence. The network knows a boundary condition. It doesn't have to learn it from scratch via the loss.
That sounds very effective if you can design the architecture right. Anything else on the architecture front?
Yes, one last thing they mention is a modified MLP architecture. It's described as a relatively simple modification to the standard MLP structure.
And what does it do?
It apparently demonstrates an enhanced capability for learning nonlinear and complex PDE solutions. So it seems to be better at capturing the intricacies of the physics compared to the standard MLP. even with the other enhancements.
Is there a downside?
The trade-off is that it typically demands greater computational resources. It's likely more expensive to train. But the guide suggests it generally outperforms the standard MLP in minimizing those crucial PDE residuals and getting more accurate results, especially for tougher problems.
Okay, so lots of tools in the toolbox there. Now, what's really compelling, I think, is that the paper doesn't just propose all these solutions in theory. They actually prove their effectiveness, right? With comprehensive ablation studies.
Absolutely. They didn't just throw everything together. They systematically tested the impact of each component across a wide range of benchmarks, different types of physics problems.
And what did those studies show?
They consistently showed that disabling any single component of this proposed pipeline, whether it's non-dimensionalization, RFF, causal training, loss balancing, whatever, generally leads to worse performance, sometimes significantly worse.
So it really demonstrates the positive contributions of each component. It's not just one magic bullet, but the combination.
Exactly. It highlights this synergistic effect. You really need most, if not all, of these pieces working together to get the best, most reliable results from PNNs.
And this careful methodology, this pipeline, it leads us to what I think is a real aha moment from this deep dive. The breakthrough they report with Navier-Stokes flow around a cylinder, specifically about vortex shedding.
Ah, yes, the vortex shedding problem. That's a classic, challenging fluid dynamics scenario.
And previous research, as the guide points out, had basically suggested that pins kind of fall short here, that they acted more like steady flow solvers and simply fail to capture the phenomenon of vortex shedding, which is this very complex, unsteady, oscillating flow pattern that seemed like a pretty big limitation for pins and fluids.
It was definitely seen as a major challenge, yeah. Doubts were cast on whether pins could handle these kinds of transient, complex flow structures.
But this guide
directly challenges these findings. They demonstrate quite convincingly that if properly used, meaning if trained using this comprehensive pipeline with all the best practices, pins can successfully simulate the development of vortex shedding in this scenario.
Wow, so they can capture that complex time-varying behavior.
Yes. It's a really significant finding because it refutes earlier limitations and shows that the capability was there. It just needed the right training methodology to unlock it. It opens up new avenues for further research in applying PNNs to much more complex, unsteady fluid dynamics problems and potentially other chaotic systems too.
That really underscores the power of getting the methodology right. It's not just the tool, but how you use it.
Absolutely. It shows how much potential these networks have when they're implemented correctly and carefully.
Okay, so let's try and recap this deep dive. We've really unpacked how these physics-informed neural networks, which have so much promise, can actually live up to it when they're equipped with this comprehensive training pipeline.
Everything from foundational steps like non-dimensionalization, making sure the scales are right,
to using specialized architectures like those random Fourier features to capture detail and random weight factorization for efficiency.
and then layering on those intelligent training strategies. Causal training to respect time, adaptive loss balancing to handle different error scales, and curriculum learning like time marching or progressive difficulty to break down complex problems.
Yeah, putting all those pieces together allows PNNs to overcome their core challenges, that spectral bias, the causality violations, the unbalanced gradients, and really start to shine.
And this deep dive, based on the expert guide, really shows that it's not just about throwing more computational power at the problem. It's about developing smarter algorithms and methodologies.
Right, and by providing these strong baselines, these proven techniques, and even a reproducible library, this work really aims to propel PN research towards more effective and reliable solutions in computational science and engineering.
It sets a new standard in a way.
It really makes you consider this, though. If these finely tuned AI models, these PNNs, can now accurately simulate something as complex and frankly chaotic as vortex shedding, what other doors does this open? What other currently intractable scientific or engineering challenges, problems we couldn't solve well before, could these refined PNNs finally unlock in the very near future?
It's a huge question. Mysteries of the universe, fundamental physics, or maybe incredibly complex engineering design problems, optimizing aerodynamics, designing new materials with exotic properties.
Things that might finally yield their secrets to this powerful combination of physics and AI. It's quite a thought.
It really is. So think about everything we've covered. What stands out to you listening in as the most surprising or maybe the most impactful insight from today's deep dive?